Hi everybody, it's Dr. Pusey. In this video I'm going to be going through the 2020 ATAR Physics exam. Okay, so for question 1 you've got a ball that's been launched vertically into the air. It tells you that it takes 4 seconds for it to reach the maximum height, which means at 4 seconds we'd have max height. I'm just writing this down to help us out. And then given the symmetry of the problem, we'd expect at 8 seconds you'd have a landing. So the first one is just looking at the displacement over time. So if we said that it had its max height at around here, I'm going to set its maximum height to about this value. It's arbitrary, it doesn't really matter. And then I want to draw a nice parabolic curve that just sort of goes over that value and sort of tries to maintain that symmetry. Now for the velocity time graph, we'd expect the maximum velocity to be right at the start because it gets launched, and then it should steadily drop until it reaches that maximum height, until it's at a velocity of 0, and then it will turn around and speed up in the opposite direction until it reaches the same magnitude of the velocity, or the same speed, but just in the opposite direction. So you can see the shape there looks pretty good. Now the acceleration, pretty straightforward one. The acceleration is the same at all times. We want to pick a value that we think will be negative 9.8, and it'll be pretty static along there. Now you probably want to use a ruler if you have one. Unfortunately for this computer I don't. And there we go. Okay, now for question 2, it says calculate the speed of an electron with a de Broglie wavelength of 1.23 nanometers. It's a very easy question. I think it was the easiest question in the exam. We get given this equation already, and then we just sub that out to get the mass and velocity. And therefore we rearrange. We got the velocity is equal to h on m lambda, and you plug in your values, mass of an electron, and the wavelength that's given in the question. You do that and you should end up with 5.91 times 10 to the 5 meters per second. And this next question, question 3, I thought it was a fairly easy one, but I know that some students are having some issues with it. So we start off with what we definitely do know, and we can work out first the energy of the photon. The energy of the photons is going to be hf, and we're given the wavelength, so we can just convert that to hc on lambda and put in our values, and we should get 3.79 times 10 to the negative 19 joules. Now that is how much energy is in each photon. Now 10 watts is the same as saying 10 joules every second, and it's asking us how many photons does it emit per second. In other words, how many photons does it emit for 10 joules? And that's where some students sort of get a little bit confused. So if we know that we want 10 joules, and we know that each photon has 3.79 times 10 to the negative 19 joules, then we can have the number of photons as just being the 10 joules over the 3.79 times 10 to the negative 19 joules. And what you should get is 2.64 times 10 to the 19 photons every second. So question 4 is one of the easier questions. You've got a physics experiment where you have a group of students running a DC current upwards through a 3.5 meter long wire. So the first part of the question is just asking to work out the magnetic field strength at a certain distance from the wire, right? So you just apply this equation here over 2 pi r, and it's giving you all the information. So mu naught 1.26 times 10 to the negative 6, and I is 2.78 amps, and we're going to divide that by 2 pi, and the radius, it's in centimeters, so it's 0.251, and what you should get is 2.22 times 10 to the negative 6 on down here. It'll be 2.22 times 10 to the negative 6. Alright, the next part of the question is looking from above, which of the following diagrams shows the magnetic field around the wire correctly? So if you give a thumbs up, what you'll notice is that your fingers will wrap around anti-clockwise. So the answer is going to be either A or D. However, D, the big difference between A and D is that D demonstrates that the distance between the field lines stays constant, when what we actually do expect it to drop much faster than that, and so the answer would be A. And in question 5, we've got a person standing on the end of a dive board. Looks like a fairly straightforward one, except the big trip up, and it even tripped me up, is that the length of the diving board is 5.2 meters. However, the distance that Emma is standing is 5 meters. So this did actually get me. So let's have a look. So if we take this hinge as the pivot point, everything's at right angles, so it makes it a bit easier. So at P, you have the sum of the anti-clockwise torques is equal to the sum of the clockwise torques. So you have RF from the support, it has to be balanced by RMG of the board plus RMG of the diver. So just help annotate that, like this part here will be the support acting up, and RMG will be the board acting down, and this RMG will be the diver acting down. So now we're just going to plug in those values, right? So the support is acting at a distance of 2 meters at Fs, and we are trying to find Fs. That's going to be equal to, so the board, the R value is going to be 2.6 because it's half of that 5.2. And the mass of the board and gravity. And the diver is 5 meters along, 40 kilos, and gravity. And what you'll end up with is that Fs is equal to 3234 over 2. Now I've got 1617, so you should end up with 1620 newtons. So for question 6, it looks pretty complicated, but just with a simple concept, you should be able to get it. So the electric field strength is equal to essentially the force on any unit charge, right? And we know, thanks to Coulomb's law, so let's just say that any unit charge is Q2, right? And we'll make Q1 the charge that we're a certain distance from. So that would mean that if we have that force, so I'm going to use Coulomb's law to derive force, so that's Q1, Q2 over 4 pi epsilon naught r squared, and we want the that force per unit charge, and in this case that unit charge is going to be Q2. And if that's the case, these two cancel out, and then it's a matter of subbing it in. So it's just 4 times 10 to the negative 18 over 4 pi 8.85 times 10 to the negative 12 and 2.25 times 10 to the negative 3 squared. And if you do that, what you should end up with is 7.10 times 10 to the negative 3. So question 6, yeah, it's a bit tricky when you first look at it, but then when you look at the equations, they all sort of works itself out. So for question 7, we're looking at this idea of magnets moving around an aluminium table. Now, aluminium is not magnetic, but it does conduct electricity. So as the magnets move around the table itself experiences a change in magnetic flux around certain points, which induces eddy currents. So the way that I'd explain this will be using the following 4 points. First, I would say that the moving magnet creates a changing magnetic field across the aluminium plate. So you want to specify that the magnet itself creates a changing magnetic field, because that leads on to the next point. The changing magnetic field induces eddy currents in the conducting material. So you want to specify that the aluminium does conduct electricity. And Lenz's law tells us that those currents that are produced will induce a magnetic field that opposes the change. So as a magnet goes over a certain part of the aluminium table, the induced eddy current will actually oppose that motion. So overall, the induced fields will create an opposing force which will slow down the movement of the magnet. And for part B, it's saying what would the velocity and acceleration graph look like? Well, looking at the graph, you can see that we'd expect the velocity to start off high, so it's either B or C, but the acceleration should always be opposing the motion, which means that it must be B. Okay, so looking at question 8, you've got a diffraction pattern being formed, and the first question says what property of light causes this to happen? And diffraction is the wave nature of light. That's a fairly straightforward one. And now it's asking us to explain it, and that's where there's 4 marks of explain in there. So we'll start off by the diffraction occurring. So we'd say that light exiting each slit will diffract or spread out. And then I would say that from those 2 waves, or those 2 waves coming from those slits, they would superimpose or overlap over each other, and they would interfere with one another. And then it has bolded the word both in the question, so I want to talk about the light and dark fringes as two different points. So I'm saying the light fringes are formed on the screen where the waves are in phase and you have constructive interference. You could also say the path difference between each wave is an integer number of wavelengths. And then I would specify that dark fringes are formed when the waves are completely or 180 degrees out of phase, and that's where you have destructive interference. And you could also talk about that in terms of the path difference being an integer plus a half number of wavelengths, so that you have two waves that are completely out of phase, and then you'd have destructive interference. So question 9 is a relativity question. It's another explaining question, and you notice it's got the equation you've got in your data sheet, but then it starts talking about the Lorentz factor, and then it's got a graph where it's sort of introducing this new variable beta. Beta just being the ratio of the speed of the observed speed and the speed of light. So it's asking you to refer to the graph when giving your answers. So I would explain it first by talking about as you'd expect, as v approaches c, the beta factor approaches 1. Or 1.0 is what I've written. And according to the equation, as beta approaches 1, then the gamma factor, so we're still looking at the graph, it approaches infinity. So if it's an approaching infinity, then we start looking at the energy equation, and we'd expect the energy equation to also go towards infinity. And since energy is required to achieve any increase in velocity, we would expect that as that Lorentz factor approaches infinity, it would mean that we need infinite amount of energy to achieve the speed of light, which is impossible. Okay, so for question 10, it's a little bit more involved, but it's definitely achievable. You've got a ball that's being hit at 37 meters a second, and they tried it with an angle of 31 degrees, and it made it 123 meters. But they want to hit a target of 135 meters away horizontally. So what you want to do is increase the angles to reach that far. So what you want to do is, if we've got a ball being hit 37.0 meters per second with a velocity of 37.0 meters a second, we know that the upward velocity, or the y component of that velocity, is going to be 37 sine of theta, where this here would be your theta, and this would be your horizontal velocity, which would be your 37 cos theta. So if we now start deriving our stuff, we first want to resolve it horizontally, right? So horizontally, we would expect that S equals ut, so the horizontal one is going to be equal to horizontal u multiplied by t. So let's put in those values. We want it to reach 135 meters away horizontally, right? And we know that the the velocity, the u vector, is going to be 37 cos theta, and t is just t. So we're going to keep that there. We're going to use this later on. So I'm going to put an asterisk here. So now vertically, what we would have is a much more complicated scenario because we have gravity being involved. So I'm just going to specify under gravity. So if that's the case, because the golf ball is under acceleration in the vertical plane, we'll need to use this equation here. SV is equal to UVT plus a half a t squared. So I can sub in those values. Now the vertical distance the ball travels, it actually ends up in the same location vertically, so we can say 0, and that's going to be equal to 37 sine theta t, and instead of a half a, I can say minus 4.9 because it's gravity, t squared. Okay, so now I've got this one too. So what I'm going to do is I'm going to rearrange this equation over here. I want to get rid of the t's, right? So I'm going to say, well, what if I say that t is going to be equal to 135 over 37 cos theta. Now if that's the case, I can then introduce these two together. Okay, so now that I have two expressions that I can use together, I've got one expression that has the equation of motion vertically in terms of t, but I don't know what t is. But I know what it is in terms of the horizontal velocity. So every time I see t in this first equation, I'm going to replace it with 135 divided by 37 cos theta. The first thing I'm going to do is I'm going to break it up into really easy steps for you to follow. So I'm going to just throw one of these onto the other side of the equal sign, just so it's all positive. So I'm going to have 37 sine theta t, is going to be equal to 4.9 t squared. So that's the first step. Now what I'm going to do is I'm going to start substituting in those values. So I end up with 37 sine theta. Now instead of t, I'm going to put in 135 over 37 cos theta, and that's going to be equal to 4.9. Instead of t squared, I'm going to put 135 over 37 cos theta. Now I could square this, but I want to be really clear about what I'm doing, so I'm going to instead just write it again, just so you can see what I'm doing here. Cos theta, right, so now I've got 4.9 t squared. So let's start cancelling things out. So this 37 here cancels with that 37. These 235s, one of them will cancel out, and one of these cos thetas will cancel out. So what I'm left with is sine theta is equal to 4.9 135 over 37 squared cos theta. Great. So now what I can do is I can bring this cos theta over, because what I'm trying to do is get that trig function, or that trig identity that we had at the top there. So sine theta cos theta is equal to 4.9 135, all that sort of stuff, 37 squared. Okay, so if I know that sine theta cos theta, that's actually equal, well, two of those is equal to sine 2 theta, right? So if I put a 2 out the front there, and I'm going to put a 2 out the front here, so now I've got this function right there. So I can say, therefore, I'm going to do it over here, sine of 2 theta is going to be equal to this. And that value there becomes 37 squared. Put that in the calculator. And what you end up with is 2 theta is equal to 75.10. So theta is going to be equal to 37.55. However, it's asking for the change in angle, which means it's asking for what is the increase in the angle that you want. So you subtract the original angle they gave you, and you make that equal to 6.5 degrees. And over here, 6.55 degrees. And there you go. In question 11, you've got yourself 2 books. You're lifting up 2 books. So the first thing it's saying is, what is the magnitude of the acceleration of those books? It's a pretty good one. You want to draw a free body diagram, I reckon. So if you've got yourself a diagram here, you have gravity's acting down. That's me 3, 9.8. Awesome. So that's one force that's acting. And the next thing it's saying is Jake's hands exert a vertical force of 16.2 newtons on the lower book. So that means he's pushing up on those books with 16.2. But he said here a vertical force each of Jake's hands. So that means it's going to be times 2. A bit tricky. And that's your upward force. So that means that the net force acting on those books is going to be equal to 2 times 16.2. Subtract the weight force, and what you'll end up with is 3.00 newtons, a very nice round number. So if that's the net force, you find the acceleration by dividing it by the mass of what's accelerating. And it's asking you for the acceleration of both of the books, so it's going to be 3 divided by 3. And what you'll end up with is 1.00 meters per second. And now we're looking at something a little bit different. What is the magnitude of the force that the 2 kilogram book exerts on the 1 kilogram book during this acceleration? So now let's look at the forces acting only on that 1 kilogram book, which is the one on the top. So we have gravity still acting on it, except in this case it's going to be 1 times 9.8. And then there's going to be another force that we want to find out what that is. But we know it's net force because we've calculated that above. So if we just write down the net force, that's going to be equal to the mass times the net acceleration that we've already calculated, and that's equal to 1. Right, that's all good, and that should be equal to the upwards force subtract the downwards force. Cool. So then we end up with the upward force just being equal to the 1 plus the downwards force, which is 9.8. So the upward force counteracts gravity and gives it some acceleration, which makes sense. We'd expect it to be 10.8 newtons. So down here, we put 10.8 newtons. Cool. Still moving down, question 12. Looks like a fairly straightforward one. So what have we got? Which is the appropriate combination of relevant fundamental force and property? Okay, so a gluon is a strong force mediator. So if you look at our formula sheet, we'll notice straight away that a gluon does not have any mass. So we would say that it must be a 1. A photon also doesn't have any mass, and it deals with the electromagnetic force. So we would say that's a 5. And the Z and W bosons, or the Z and W bosons, are both part of the weak force. And if you look at your data sheet, you'll notice that they do actually have a mass. So both of them would be the same. Which of the fundamental forces has the longest range of interaction? So we know that the weak nuclear and the strong nuclear have a finite distance over which they act, whereas electromagnetic and gravity have an infinite range. Now, because gravity is not here, it makes our choice pretty easy. So write down electromagnetic. And that's section 1 done. So question 13 is the first of the problem-solving section. It's sort of a modified version of your classic oil drop experiment. So at the beginning, there's no potential difference applied between the plates. And instead, the observation is that the oil drop is falling at a constant velocity, so it's sort of at a terminal velocity. So the downward force acting on it is still going to be weight, but if it's falling at a constant velocity, there is going to be an upward force equal in magnitude, but it's not going to be the electrostatic force. Instead, it's probably going to be drag. Okay, so if we keep moving through, what we're doing now is we turn on the voltage supply so that we can have that drop suspended. Now, it's telling you the potential difference and that sort of stuff, but the first question that's asking you is name the two forces acting on the oil drop. So we're not drawing the free body diagram in this particular case, we're just writing them down. So you can write either weight or gravity, I'm sure. And the next force will be the electrostatic force. Now, it's given you a simple plug and chug. If the plate separation is 7.71 mil, what is the electric field strength? So we've actually used this equation. There we go. And the voltage is 346 volts. And the distance is 7.71 millimeters, so 0.00771. Put that in my calculator, and I end up getting 4.49 times 10 to the 4 volts per meter. And calculate the electric charge of the oil drop. So we're going to go back to that same formula. E equals F on Q, which is equal to V on D. If we rearrange that, we end up with Q equals FD on V. And we also know that in this particular instance, the electrostatic force must be equal to the gravitational force, which is equal to mg. So what I'm going to do is for F here, I'm going to sub in that value. So we end up with Q is equal to, not value, the expression mgd over V. And now I can just put in my numbers. 346, and you should get 1.50 times 10 to the negative 19. There we go. Now this next part's a little bit interesting. We've got students repeating the procedure and getting different values. And it's possible that they have different numbers of electrons on the oil drop, which is, yeah, it's a bit strange. Anyway, so it's trying to get you to look at the data and think, okay, well, based on this data, what would the student estimate the electron charge is most likely to be? So the key here is that it's saying possibly carrying different numbers of electrons. And what they're hoping you'd come up with is to look at the data and go, well, okay, well, if I look at there seems to be a common factor here. So if I was to say, that looks like a 6, and that looks like a 3, that's like a 4.5, this one's a 7.5, that's a 3, that's a 7.5. Okay, so what would the common factor be here? Well, this 6, if we were to say it was 3, that would be 1. If we were to say the charge of an electron is 3 times 10 to the negative 19, that would be twice as much, but there's a 4.5 there. So really the conclusion you should be coming to is that this is actually 4 times 1.5, and this one's 2 times 1.5, and this one's 3 times 1.5, and this one is 5 times 1.5, and then we have 2 times 1.5, and this one again is 5 times 1.5. And what they sort of want you to come to the conclusion of is to say, well, this is the common factor, this number, this 1.5. So that tells me, if I was estimating, that the answer would be 1.50. Well, that's an estimate, so it should only be 2 sig figs times 10 to the negative 19. And we know the accepted value is 1.60 times 10 to the negative 19, so that seems like a reasonable estimate to make as well. But yeah, interesting. So in question 14, we've got muons and antimuons, and we're looking at standard model stuff at the beginning, and then we get into relativity. So the first one is we need to find this mystery particle. So if we look at the electron charge on this side of the equation, we've got a positive 1, and at the moment it's 0. So we need to have electron charge of positive 1 on this side. And over here we have a lepton number of negative 1, and it is currently also 0, which means that this side is going to need to be negative 1. So we need something that has a charge of positive 1 and a lepton number of negative 1. So since we're dealing with a lepton number, then I would suggest that it must be a positron, because a positron has a lepton number of negative 1 because it's antimatter, and it has a charge opposite of an electron of positive 1. And now it's talking about muons, and it starts talking about all these things with speeds and stuff like that, and it's sort of giving lots of figures, but the important thing is it says in their own frame, muons have a mean lifetime of 2.2 times 10 to the negative 6 seconds, with some lasting up to 3 times 10 to the negative 6 seconds. So, you know, they have a lifetime, but some of them will last longer, some of them will last not as long, and that's sort of an important concept here. But the question most likely, or mostly, wants you to deal with the mean lifetime. So we're going to start with a pretty easy question using non-relativistic physics, calculate the mean distance they'll travel in that time. So that's pretty straightforward. S equals Vt, and you sub in those values, 2.991 times 10 to the 8, multiplied by that mean lifetime, so 2.2 times 10 to the negative 6. And what you should end up with is roughly 658 meters, which is much smaller than, say, the distance it would travel if it came from the upper atmosphere. And now it's saying calculate the mean lifetime of the muons traveling at 0.997 C as observed by the Earth. So now it wants us to get that time and essentially dilate it. So we start with this equation over here from your formula sheet, and you just sub in your values. So you get that mean lifetime again, and of course the C's all cancel out and stuff like that. 7 squared. And what you should end up with is 2.842 times 10 to the negative 5. So down here in seconds, just 2.84 times 10 to the negative 5. Put that across. There we go. And now it's saying what is the actual mean distance travelled by such muons. So now we've got the dilated time, and we can essentially sub that back into the original equation. So we use S equals Vt. And now we're going to be using the same velocity, but we're going to use the dilated time. I'm going to use a little bit more precise of a value for myself, but it shouldn't make much of a difference. And what I got was 8,500 meters. So if I put that in 3 sig figs, and it also says in kilometers, it's 8.50 kilometers. Okay, so now we're sort of looking at a better value. But if you look at the top there, it says that it's 10 kilometers. And that's what this next question is sort of talking about. It's saying, using the information from the question, explain why a small number of muons reach the Earth. So I would probably go along the lines and say some muons have a higher than average lifetime. Some also have a higher than average speed. So those are two things that could, so the speed itself could also affect the lifetime, right? So that also increases time dilation. So therefore, a small number, not all of them, but a small number or a small portion will reach the Earth's surface. Okay. And now it's saying, with the use of a calculation, explain why these muons reach the Earth from the perspective of the muons. Okay, so the muon doesn't see its own dilated time. So how does the muon, how can we justify that the muon will make it to the Earth according to the muon? So now we need to talk about the muon's perspective. And this is your classic length contraction. So we have, according to muon, the length, or in this case the distance that it's traveling to the surface, contracts. So now put in the equation, because it says use a calculation, right? So length is equal to L0. Put that all in. So the length I'm supposed to travel is 10 kilometers, but I'm now going to contract that. And if I do that, I end up getting 0.774, and that's in kilometers. So that's equal to 774 meters. So according to the muon, I'm actually only traveling 774 meters, right? So the amount of time that it would take, or the amount of time that I have to get there, basing it on that mean speed, according to the muon, I can just rearrange that equation, S1V, and I end up with 2.59 times 10 to the 6 seconds. So if you remember, some of them have a lifetime of 3 times 10 to the negative 6 seconds, right? So that would mean that those ones would actually have enough time to get there. So you just sort of summarize. So you'd say this is just above the mean, or you can say it's below the maximum lifetime. So some muons will reach the Earth's surface. Cool. Okay, so in question 15, it's actually 3 mini questions, and all of them are about using the correct velocity addition formula. So the first one is calculate the velocity of Harper as measured by ATAR. Now, one weird thing about this question in general is that they want you to take this direction as positive. Now, the reason they've done that is so that your answers aren't so strange, because a lot of them become negative. But let's just go with that. Okay, so it's asking for the velocity of Harper as measured by ATAR. Now, that would mean that ATAR in this particular case would be V and Harper would be U. Now, the reason ATAR is V is because this individual is moving and observing, because we're asking how fast Harper is according to ATAR. So I would start by writing down what I know. So I know that V is moving in the opposite direction at 0.5 c. And I know that according to that same observer who's measuring ATAR, then Harper's also going in the opposite direction, which is a positive number, at 0.750 c. And because we want to know Harper's velocity in according to the moving reference frame, that is U dash. So that's what we're after here. So it's not terribly difficult to apply. The mistake, if anyone makes mistakes, is usually done by now, because you might have misinterpreted the question or put the wrong value in. So if you put that through, end up with that, C over 1 plus 0.5 c times 0.75 c over c squared. This is the only time I'm going to do this, but those c's will cancel out that c, so you're just left with this c here. Oh, that's a c too. And what that ends up with is 0.909 c. So in part B, we have Harper firing a missile with a velocity of 0.6 c with respect to her in the direction of ATAR. So that would mean that we are now being given U dash, because we're being given the velocity of an object according to something that is moving. So V in this case is going to be Harper, because Harper's observing the missile, and Harper is moving the same again at positive 0.750 c, and U, which is the missile, We don't know what the missile is according to the observer of Earth, but we know what the missile is traveling at according to Harper, and we know that it's in the same direction at 0.600. So again, we apply it using the relevant formula. Which one don't we know? And it should look a bit like this. Over that, over c squared. I'm not going to do the simplification in this case. It's just going to be 0.750 plus 0.600 over 1 plus 0.75 and 0.6. Because if you remember from the previous part of the question, they cancel out. And if you put that in your calculator, what you'll get is 0.931. And again, mistakes are usually made over here when you're assigning the variables. So my tip that I always give to everybody is first find out what the moving reference frame is, and everything else should fall into place. Now this one can be done a number of different ways, two main different ways. So it's asking for the velocity of the missile as measured by ATAR. So because of that, I'm going to say that ATAR is the moving reference frame, because that is where the measurement's being made, their observation, and we can remember it's negative 0.50 C. And we know, and that 0.500 C is relative to an Earth observer, and we know the missile speed according to an Earth observer now, because we worked out what that was in part B. So 0.931 C. Again, it's going left, so it's positive, and we want to know what it is according to ATAR. So come over here and we just apply the same equation. And again, you could do this from a different bunch of perspectives, because you've got lots of details now, but this is the way that I just go about doing it anyway. 0.931 C, and if you do that, you should end up with 0.976 C, and there you go. And now looking at question 16. You've got a generator question. So it tells you how many turns, it tells you the magnetic field strength and the frequency, except the frequency is an RPM. The first part A, it's interesting, it's worth 5 marks, but it's a very straightforward question. So maximum EMF is going to be equal to 2 pi NABF. Okay, so we have the 2 pi. N is your 150 turns. The area, so it's a square coil. I think it was, what was it? It was 6 centimeters squared, so 0.06 squared. And magnetic flux density is 1.85 times 10 to the 2 millitesla, so I need to multiply that by 10 to the negative 3. I'm sure that will trip a few students up. And the frequency is going to be your 240, but that's in RPM, so I need to convert that by dividing that by 60. Alright, now that's done. You put that in your calculator and you end up with 2.51 volts. I'm not sure what the rest of the space is for. I guess if you do the conversions separately. But yeah, that's a pretty easy 5 marks. And the next question is calculate the RMS of the voltage produced. Again, it's a pretty easy mark, so the EMF RMS is going to be equal to the peak over root 2, so it's going to be 2.51 over root 2, and what you'll end up with is 1.78 volts. Moving on to the next part, it's asking to explain why the force varied as the handle went through one rotation. So to answer this question, I'd first point out that the EMF produced by the generator is changing throughout each rotation. So depending on the orientation of the coils, the change in flux is actually varying as well. And that can be shown with the flickering of the light bulb. So when the maximum EMF is produced, more energy is being converted from mechanical energy, which means it becomes harder for us to rotate as we need to exert more energy to make that turn happen. And then we can talk about how this is due to Lenz's law, where the induced current produces a magnetic field to oppose the motion. And part 2, in what position was the plane of the rotating coil relative to the field when the light bulb went out? So what I'll do is I'm going to show you what I mean by drawing a nice little diagram over here. If I have, that's a terrible diagram. But if I have my magnetic field, there we go, and then I'm going to put my coil in there like that. Okay, all good. Now let's just say that I'm going to be rotating it this way. Now in the orientation that I've got it, notice that the poles, or the conducting wires, are actually going to be moving parallel to the field. And because they're moving parallel to the field, then they're actually not going to be inducing any EMF at all. And if that's the case, you're not going to have any current flow, and the light bulb will not turn on. So the question's asking what the plane of the coil relative to the field when the light bulb went out. So that's asking for this plane here relative to the field. You notice that the plane is perpendicular. So that's because the conductors that are inducing the EMF are moving parallel, but the plane itself is perpendicular. So my answers would be perpendicular to the field, where the lengths of the coil are parallel, they move parallel to the field. If they're moving parallel to the field, that means no EMF is generated. Now you can also explain this in terms of the rate of change of flux going through the coil. If you have a look at the diagram, any small movement of that coil would not really result, or effectively result in a zero change of flux going through the coil, because it's already capturing the maximum amount of EMF. So in that particular case, no EMF is produced. Okay, question 17. A satellite is orbiting the Earth. It's given you its altitude, and it's asking for the period of the satellite. So because it's given you the altitude, the first thing you want to do is work out what the radius is, the orbital radius. So that would just be the radius of the Earth plus that 4 times 10 to the 3 times 10 to the 3 again, because it's in kilometers. And what you should end up with is 6.37 times 10 to the 6 plus 4 times 10 to the 6. And that is equal to 1.037 times 10 to the 7 meters. Okay, so with that result, we can just throw that straight into Kepler's law. 4 pi squared over g, mass of the Earth, r cubed, times 10 to the 24. Okay, and that ends up being equal to 1.1056 times 10 to the 8. Now that's t squared. So your t, your period, is going to be equal to the square root of that. .0514 seconds, which is 175 minutes. That's asking for the number in hours, so you divide that by 60 and you'll get 2.92 hours. Okay, and the next part of the question is, they want you to refer to Kepler's law again, his third law. Describe how a straight line graph could be generated using the same two variables. Right, so let's just start by writing down what we know about Kepler's law. The law there is 4 pi squared on g m r cubed. Right, so we know, therefore, if you look at this equation, that your t squared is going to be proportional to your r cubed. Essentially, that means that if you plot t squared on your y, for example, and you plot r cubed on your x, so you need to square the period and cube the radius, then you should get a straight line where this becomes your gradient. And I imagine that's what we're going to be moving through in the next part of the question. Explain how you can use the gradient of this straight line and Kepler's third law to estimate the magnitude of the Newtonian constant of gravitation. Right, okay, so let's go back to that point. T squared is equal to 4 pi squared on gm r cubed. Right, so in this, we could explain it a couple of ways. We could go up here and say, well, if that's your y and that's your x, that's your m value, so your gradient. Or we could come back here and say, okay, well, when we do that graph, if we worked out the gradient of that graph, that will be equal to rise over run. Now the rise would be your t squared, you change in t squared, and your run would be r cubed. And if you go back to that equation here, that's equal to 4 pi squared over g, mass of the Earth. We'll then need to point out that since mass of the Earth is a constant, then we can say, and rearrange it, and say that g is going to be equal to 4 pi squared over the gradient multiplied by the mass of the Earth. And there we go. Okay, so for question 18, you've got a moments question. You've got a fairly straightforward scenario. You've got a drawbridge that's just been lifted, so there's going to be a weight force acting down, and there's also going to be a tension force acting along here. It's not actually hitting this at the moment because it's saying it's just being launched. I'm going to use the hinge as my pivot point, which is the obvious place to take it, and then start from there. So at P, the sum of all the anti-clockwise torques is equal to the sum of all the clockwise torques. So the anti-clockwise torques will be the tension, so it's just going to be RT sine theta is equal to this side, it's going to be RMG sine theta, which if we just go through that again, we've got RVO in this case is going to be 6, and T sine theta is going to be T and sine 35, and that's going to be equal to 3 because it's acting halfway along. mg, which is going to be a 500 times 9.8, and because the force is already acting perpendicular, there is no need to worry about the sine theta, it goes to 1. So then we rearrange the equation, we get T is equal to 14700 is equal to 3.441, and we should get, well, I got 4271 and 3 significant figures, 4270 newtons. And the hard part is here, so it's asking to calculate the reaction force of the hinge on the drawbridge at this point. Now there's a couple of ways that you could do it. Because it's asking for an angle, I'm less inclined to use the sine rule or the cosine rule. Instead, I'm just going to look at the vertical and horizontal components. So what I'm talking about is if I was to sort of draw the free body diagram of that bridge, there's a force acting down here, and I know that now is 4900 newtons because that's mg. I also know that there is a force acting this direction, and that's, I know the magnitude of that is 4270 newtons, or it should be 4271, doesn't matter. And we have a reaction force here. Now we don't know the angle and we don't know the magnitude, so we're just going to sort of draw a rough guide there and say, yep, that's what you want to do. So we have to start with the assumption that for this whole thing to be in equilibrium, the sum of all the forces must equal 0. So let's talk about the reaction force horizontally. So horizontally, we have just one force that's contributing to a leftward force, I suppose. So that would mean that the reaction force in the horizontal direction must be 4270 cos 35, and that would therefore be equal to 3500 newtons, and that's acting to the right because at the moment the tension is acting towards the left. Okay, so that's the first. So that's your first bit. Now we know the horizontal forces, let's start looking at the vertical forces. So the vertical reaction force, that has to basically balance out all the vertical forces there. And we've got a gravity force acting down and the tension force is acting up. So what I'm going to do is I'm going to suggest that up is going to be a positive value. So I'm going to start with the upward tension force. So 4270 sine 35. And I'm going to subtract the gravitational force, and what I end up with is 2451 newtons upwards. Great, so now I have what the two component vectors for the reaction force. So the reaction force is acting up and to the right, so I'm just going to draw a rough diagram here. That's my reaction force. That's going to be made up of two component vectors, this one and this one, where the one over here is 3500 newtons and this one here is 2451 newtons. If that's the case, I can work out the magnitude of R is going to be the square root, so using Pythagoras, 3500 squared plus 2451 squared, and I get 4270 newtons, which is really interesting, the fact that that is equal to the tensional force. I'm not sure whether they did that on purpose, but that's not always the case. And then we have our theta, and that's going to be the inverse tan of 2451 over 3500, and that would be 35 degrees, and that is this angle here, so that's already relative to the horizontal, so I can just put those values in, 4270 newtons at 35 degrees to the horizontal, or 35.0 And there we go. Question 18 comes under attack, and they start to raise the drawbridge. Okay, so now they're raising it, and it's at an angle of 15 degrees above the horizontal. The angle between the drawbridge and the rope. Okay, so let's just start drawing what we see here. I think it'll be really helpful. So the drawbridge is now being raised like so. We've got tension, and it's now saying the angle between the drawbridge and the rope is 40 degrees. So there's your tensional force, and that is now 40 degrees. Great. And it says the 95 kilogram soldier being chased jumps onto the very end of the drawbridge. So now there's another force acting down of the soldier, and that's his 95 kilos, so 95 times 9.8. And the drawbridge itself, of course, is now acting down, and that's equal to 500 times 9.8. Cool. Now the lengths that we're working with is, we'll say this one here is 3, and we know that the one acting over here is 6. They're the only distances I have to worry about, I believe. We can just go through and start solving this question. So it's asking for the tension in the rope again, and now the question becomes a little bit more complicated because there are no right angles. However, one important piece of information it's given me is that it's at an angle of 15 degrees above the horizontal, which means this angle here is 15 degrees, which means, so I like using the perpendicular force method. That means that for me, this angle and this angle are both going to be 75 degrees. 75 degrees. And if that's the case, I might get rid of that purple line, it's a bit confusing. If that's the case, we can start solving. Right, so at P, start off with your assumptions, just in case you get mistakes. The markers love seeing that you know it's a torques question, so they love showing the requirement for a system to be in equilibrium, which is this. If that's the case, I'll start fleshing that out. RF sine theta is equal to RF sine theta of the the soldier, and I'll make the center of mass, and then this one will be the soldier. To make that nice and clear, I'm just going to annotate that. So I'm going to say tension over here is equal to the center of mass plus the soldier. Right, so now the tension acts at 6 meters along, tension sine 40. Center of mass acts at 3, 500, 9.8. In this case, it's now also sine 75. I'm going to need more space. And that's going to be plus. Soldiers at the end, 6, 95, 9.8, sine 75. Right, put all that in, and I end up with 19594. This start over here is 3.857, and you end up with 5,080 newtons. And there you go. Okay, so looking at question 19, which is the graphing question of this paper. It's actually a fairly straightforward graphing question, which is really good. That Hubble's law. I've already drawn in the points, and I've done the line of best fit. So a couple of pointers would be to, they've already given you the scale, which makes things really easy too, which is great. So what you want to plot your data points, and then grab a ruler. Make sure you do have a ruler to get your line to best fit the data. So you want to have a pretty good judgment of this sort of thing, and with practice, you'll get really good at it. And the next step with this line of best fit would be to start looking at finding the gradient. Now I believe it's got here, it even specifically says use 2 non-data points. And that's a given. You shouldn't use data points when working out your gradient to calculate Hubble's constant. Circle the 2 points you've used and give your answer to 2 significant figures. So a lot of the information here is actually very specific. So whenever you do a graph question, you should make clear the points that you use. And they're telling you to do that by circling them, and you should also give your answer to 2 significant figures, and they've made that very explicit here as well. So you can be sure that they will have marks allocated to the fact that you do those things. And if I remember the feedback from the examiners correctly, they certainly did notice that despite this, students didn't actually follow those instructions. Okay, so when I start finding my gradient of my line of best fit, what I do is I start in the bottom left corner and I move my way up. And what I've identified is that about here, my green line cuts really nicely into part of the grid lines, right? And I can write down where it cuts those grid lines, so 5.5 and 0.25 in the y-axis. And then over here, I can see that it cuts pretty nicely about there, and that's at about 32.5 and 2.95. Now the key here is just to not pick 2 points that are close together. So when you're picking your points, don't select this point and this point. You want to pick 2 points that are very, very far away from each other. Right, so now I can work out my rise and run. So my rise is going to be the 2.95 subtract 0.25, and I get 2.7. And my run is going to be 32.5 subtract 5.5. You don't need to have your working here, I'm just doing it so you can see what's happening. And I notice that they're actually a good ratio of each other. But let's see what happens down here. So it says use 2 non-data points, blah, 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 circle the 2 points and give your answer to 2 significant figures. So rise over run is going to be equal to 2.7 over 27. And I will therefore get 0.10. Now, it's in kilometers per second per megaparsec. Just want to make sure that we've got kilometers per second times 10 to the 3. Is that what we've got there? Times 10 to the 3. Great. And megaparsecs. Good. That all suits nicely. So that means I don't have to do any unit conversions. That's just going to be 0.10. So notice that I have to make that 2 significant figures if I want to get full marks. Now, in their marking key, they accepted 0.095 to 0.105. So they accepted that range of values there. If you're outside that range, you would have missed a mark. Moving on, the galaxy, blah, blah, convert this distance to megaparsecs. Okay, looks like pretty easy marks. So to get it in megaparsecs, you just want to get the 7.42 times 10 to the 7. And there's a unit conversion in your data sheet, 3.26 times 10 to the 6. And that ends up being 22.8. But then the plot thickens, because the reason they get you to do that is because they want you to use your line of best fit and that value to calculate the observed red-shifted wavelength emitted, right? So there's a fair bit of stuff to do. So we start with the equation that they've given you at the top. It's this, the change in wavelength over the wavelength at rest is V on C. Now, the graph tells us that for NGC 2013, it is at 22.8 megaparsecs. So I'm going to go up and I'm going to look for 22.8 megaparsecs. Okay, so 22.8 would probably be around here. I'm going to go ahead and follow that up. And it hits about here with my line of best fit. So we're looking at around 2 times 10 to the 3 kilometers per second. So this is the value that it falls in. So coming back down to my number here, so from the graph, this value here, the velocity, 2.0 times 10 to the 3 kilometers per second, or I can say that as 2 times 10 to the 6 meters per second, just to try and, there's a lot of places you can get confused here. So now I can put that into the equation and say that the change in wavelength is going to be equal to 2 times 10 to the 6 over 3 times 10 to the 8 multiplied by that lambda naught, which is given here as 840 nanometers. And what I end up getting is 5.6 times 10 to the negative 9 meters. So that's the change in the wavelength. It's asking for the observed wavelength. So the observed wavelength becomes lambda naught plus the change, 6 times 10 to the negative 9. So what I write down will be 846 nanometers. Okay, cool. So part D is talking about a spiral galaxy that's close to Earth, and when you look at it edge on, one of the velocities was measured was positive and one was negative. So they're sort of asking us to explain how this could occur. So if you consider circular motion, you'd expect one side of the orbit to be traveling in the opposite direction to the other. So this is how I've answered it. I've said this would occur if the velocity on one side of the galaxy was towards the Earth and away from the Earth on the other side. And that's consistent with orbital motion within galaxies where one side moves in the opposite direction to the other. Now, if it was a spiral galaxy that's close to the Earth, it would not be moving very fast away from the Earth. So due to the expansion of space, I wouldn't expect it to be traveling at a high recessional velocity, which means the side moving towards the Earth would still be blue shifted, because it actually, as a whole, it wouldn't be moving away from Earth because it has a much reduced effect of the expansion of space. So you could say that the speed of one side of the spiral galaxy is greater than the recessional velocity of the galaxy itself. So the light is still going to be blue shifted, because overall there still is a positive velocity. Okay, so question 20 is on cyclotrons, where you have particles that are accelerated across a gap and then they turn around in this sort of D-shaped pattern, like little semicircles, due to strong magnetic fields. And the first question asks about what would you need to do to the cyclotron if you were going to be using negatively charged particles rather than positively charged particles. And they've said they need the particles that come out from the same location. So in order to do that, what you should essentially do is just change the direction of the magnetic field. So by changing the direction of the magnetic field, then the force experienced by an oppositely charged particle will be in the original direction. So if you reverse the charge, you reverse the direction of the force. So if you change the magnetic field at the same time, then you will correct for that and you will have the same outcome. And question part B is calculate the wavelength of the photons produced in the annihilation described above. So you've got a positron and an electron coming together and they form two photons. So the first thing I'm going to do is I'm going to work out, well, that's actually a very easy one, isn't it? So you just start with this equation, hc on lambda, and your lambda is going to be equal to hc on the energy of the photons. So the only difficult part, I suppose, would be understanding that you need to convert those kilo electron volts into joules. So 34 times 3 times 10 to the 8 over 511 times 10 to the 3. That's kilo electron volts. Now to get it into joules, 6 times 10 to the negative 19. And what you should get is 2.43. Oh, that's a terrible 3. 2.43 times 10 to the negative 12. And to which part of the electromagnetic spectrum does the photon belong? If you look at your data sheet, there's actually two sections that sort of get covered there. So you could either say, or both, you could say gamma rays and X-rays. And the next question says, why increasing the strength of the magnetic field, how would that increase the velocity of the particles leaving the cyclotron? So I'd start with the equation R equals mv on BQ, and mention that if you increase the magnetic field, that will reduce the radius. So essentially that will tighten up that spiral, which means that the particles would do more orbits before they exit. And if they do more orbits before they exit, then they'll cross the accelerating gap more times, which increases the overall acceleration of that particle. And by increasing the overall acceleration of that particle, you will provide a greater final velocity. And the next question is, explain why the voltage across the Ds must alternate. Okay, so if you've got charged particles being accelerated in alternating directions because they're going to be going up and then back, that means you need to change the polarity of the plates and you need to reverse them every half revolution. That way you'll be accelerating them in the direction of their motion. Okay, so part 2 of that question is the only one that I have a minor issue with, and that is to derive an expression for the cyclotron frequency, which explains why it's independent of the velocity of the particles and the radius of the circular path they follow. So I'm going to start by equating the centripetal force, mv squared on r, to the magnetic force, qvb. And then I notice that one of the v's will cancel out, so I end up with mv on r is equal to qb. And you could have done this using the formula in the data book as well. But I also know that for a circular path, the velocity of the particle is going to be 2 pi r on t. So if I now sub that in, I end up getting 2 pi r m on r, t r. Oh, it's not a very well drawn, I'll try that again. On t r. And that's going to be equal to QB. Rearranging that to get T by itself, I end up with T is equal to 2 pi M on QB. Now that I've got the period of the cyclotron, I can work out the frequency, because frequency is just 1 over the period, and that's going to be equal to QB on 2 pi M. And now that once I've gotten here, I can say, therefore, the frequency, notice in that equation, there is no velocity and there is no radius. So the frequency is independent of particle velocity and radius of circular path. So just bring it back to the original statement. Now here's the issue, right, is I interpreted the cyclotron frequency, if I go back to the diagram, as the frequency of how many full rotations it does. So 1, 2, 3, right? But the problem is that in the question, they actually say here that it's how often the electric field between the D's reverse, but that's not technically the period or the frequency. So if I come back here to here, so if we look at this waveform, it reverses. So one period would be between here and here, which means it's going to be reversing once, twice, and then once, twice. So it actually will reverse twice per orbit. Now, I guess the question is, well, who's right and all that sort of stuff. Now, the derivation that I've done makes sense to me, and if you hop on, say, Wikipedia and look up cyclotron frequency, that's the equation you're going to get. But in the marking key they've got, because for one reversal, the velocity actually ends up being just pi r on t, because it's only going half that distance. And if that's the case, you should end up with t is equal to pi m on qb. Therefore, the frequency is going to be equal to qb on pi m. So that's the answer, or that's the derivation that we have in the marking key. So I was a little bit miffed about it, but I contacted one of the markers who has told me that they accepted both answers. So, you know, it doesn't. I guess in this case, it doesn't really matter. Okay. And the last question is about wind turbines. So the first part of that question is asking why you need a step-up transformer to generate the voltage before transporting the electricity. So I would sit on the following points. I would first say that the power lost on a transmission line can be given by P equals I squared R. So if you increase and then you want to also point out that if you increase the voltage, you can conversely reduce the current if you still want to provide the same amount of power. So you mentioned P equals VI, so if you increase V, you can decrease the I. So by reducing the current passing through the lines, by increasing the voltage, the power loss is reduced. And I've just referred to that equation again. And this improves the efficiency of the transmission lines. Easy. And part 2 is just asking to work out the output voltage of the transformer. So you're just going to use your transformers equation. So you start with N1 on N2. It's going to be equal to V1 on V2. So solving for V2, you end up with V1 multiplied by N2 on N1. So that's 690 times 2500 divided by 100. On my calculator, I got 17250 volts. In kilovolts here, you want to put 17.2. Cool. So question 21 is asking for a specific reference to the text and explain why the pitch of the rotor blades is changed by the operators of the turbine. Okay, so in the text it clearly says that the power input needs to match the power output. And the power input is from the wind and the power output is from the turbine, is at the turbine. So if you want to have a constant power output, you need to make sure that your blades for the turbine are rotating at a constant speed, and that means you need to deal with changing wind conditions. So therefore you go into bit deeper, you say, okay, well, changing the pitch or the angle of the blades, that controls how much wind energy gets collected, and that will regulate the forces on the blades in order to achieve a constant rate of rotation. So this particular question is asking you to make a number of references to the article. And part C is giving you, telling you the blades are 60 meters long and an average side turbine is operating at 0.2 hertz, and asking you to estimate the speed of the center of mass of one of the blades, right? So I would start drawing a diagram personally. So if I say, you know, there's my center of rotation, I draw my blade, something like that, right? And I'm gonna put the blade here, right? Now, I know they're a little bit picky about this in the marking key. So if you go up here and have a look at the blades, notice how they're larger closer to the base. That means that the expectation is that you place the center of mass closer to the rotational pivot, right? So my estimate is 20 meters. So if you chose 30 meters, you would have lost a mark there, which is a bit unfortunate. And the total blade length is 60 meters. Okay, so if that's what we've got, now it's asking you to estimate the speed of the center of mass. So now that you know the radius, or now that you're estimating or assuming the radius is 20 meters away, so the velocity is going to be equal to 2 pi r on the period. And period is 1 on frequency, so you can just say it's 2 pi r times the frequency, and then just put in those numbers, 2 pi r being 20. Now you might have chosen 25, and that would have been fine. 0.2, and that's equal to 25.1, but because it's saying estimate, I need to give my answer to no more than 2 significant figures, so I'm going to go ahead and say it's 25 meters per second. Okay, and the last bit is draw the weight forces acting on the blades. So again, you want to come out but not too far, you don't want to go halfway, and you draw your weight vectors in, and they should be all the same length and with the ruler facing down. Okay, I could have done better, I reckon. Anyway, so I need to show mathematically that the turbine is balanced in that position. So I'm going to use this center point as my pivot, and I know, looking at this angle here, that angle there is 30 degrees. So the weight force on this blade and this blade will be acting at an angle of 30 degrees. So I can start by just saying, okay, well, about the center, I want to work out the sum of all the torques. And I'm going to say clockwise is positive, right? So that means the torque from, I'm going to put W1 for weight 1, and W2 for weight 2, and W3 for weight 3. So the torque from weight 1 plus the torque from weight 2 plus the torque from weight 3, ideally it'll be equal to 0, but I'm just going to see what happens, right? So if I keep going through, then the torque from weight 1 is going to be anti-clockwise, so it's going to be a negative R1, weight 1, so the R being the distance. Now what we'll find later on is all the radiuses and weights are the same, but we'll just keep going with this. And the other two torques are clockwise, and they act at an angle of 30 degrees, so it looks a bit like this. Okay, so now I can start pointing out that R1 is equal to R2, and that's equal to R3, and I can also point out that the weight from 1 is equal to the weight from 2, which is equal to weight from 3. So if I put that through, I end up with negative RW plus RW sine theta plus RW sine 30. Okay, cool. Now I can go through. I've got some W's there that I can bring out, and the R's I can bring out. So if I bring out the R and the W, and I say, okay, well that means I've got negative 1, and I've got a plus sine 30 degrees, and I've got another plus sine 30 degrees. Great. So sine of 30 degrees is actually a half, right? So that means that I've got RW negative 1 plus a half plus a half, which is equal to 0. Therefore, system is balanced. And there we go, and that's the end of the exam.